For the past 241 days, NASA astronaut Chris Williams and Roscosmos cosmonauts Sergey Kitskov and Sergey Mikv have lived and worked aboard the International Space Station. Their mission was a pursuit of precision, involving the growth of uniform semiconductor crystals and the development of DNA-inspired cancer treatments in the silence of microgravity. Returning home requires moving from that silence into a physics crisis. The crew is currently locked in an orbit traveling at 17,500 miles per hour, and they must shed every mile of that velocity before they touch the ground. This data shows the profile the Soyuz MS-28 spacecraft follows to survive. It is a precise, timed sequence designed to systematically bleed away that extreme kinetic energy. Safely returning astronauts to Earth is a violent physics problem. To stop, the spacecraft must intentionally exchange its orbital speed for thousands of degrees of atmospheric heat and friction. The first stage of braking is the de-orbit burn. After undocking from the station, the Soyuz spacecraft flips backward to point its main engines against its direction of travel. The engines fire for exactly 4 minutes and 42 seconds. This retrograde thrust only slows the ship by 128 meters per second. While that seems minor, this specific decrease is enough to bend the ship's trajectory out of a stable orbit and pull it down toward the upper atmosphere. This leads to Stage 2, aerodynamic braking. At 4:59 a.m., the spacecraft pyrotechnically separates into 3 distinct modules. Only the central descent module is equipped with a heat shield. The orbital and propulsion modules are sacrificed, left to incinerate in the atmosphere. As the capsule hits thicker air, it enters the plasma regime. Atmospheric friction superheats the exterior to 2,500 degrees Fahrenheit, creating a plasma bubble that blocks all radio communication with the ground for 5 minutes. During this window, the atmosphere acts as a massive brake pad. It strips away thousands of miles per hour of speed, while subjecting the crew to 4 Gs of force. The blackout ends when an Antonov aircraft near the landing site picks up the spacecraft's beacon. At 41,000 feet, the mechanical braking phase begins. In just 20 seconds, barometric sensors trigger a sequence of pilot and drogue chutes, which finally extract the massive 1,000-square-foot main parachute. This massive orange and white canopy creates enough drag to slow the capsule's fall to just 16 miles per hour. As they drift, the crew purges the ship's remaining hydrogen peroxide and oxygen fuels. This venting appears as a white vapor trail, clearing out combustible gases to make the capsule safe for recovery teams to approach. But 16 miles per hour is still too fast for a human spine to absorb. The final stage, explosive braking, occurs exactly 1 meter above the ground. 6 soft landing engines fire simultaneously. They blast downward to arrest the capsule's speed to 3 miles per hour, a fraction of a second before impact. With that final blast, the journey concludes. The spacecraft has successfully converted 17,500 miles per hour of kinetic energy into a standstill. Once on the ground, it is common for the charred capsule to roll onto its side in the dirt, marking the end of its 102 million-mile mission. But while the engineering sequence was a success, the astronauts inside face a biological tax. After 8 months in microgravity, they cannot simply walk out of the hatch. Search and rescue forces must physically lift each crew member from the capsule. They are carried directly to medical chairs to begin the slow process of readapting to the weight of their own bodies. Just hours ago, Chris Williams was conducting high-level semiconductor research in a weightless laboratory. Now he is entirely dependent on the recovery team to help him navigate the pull of Earth's gravity. Completing the 102 million-mile journey of the Soyuz MS-28 required more than just distance. It demanded a 17,000-mile-per-hour deceleration, surviving 2,500-degree heat, and the controlled destruction of 2/3 of the spacecraft itself, a sequence that remains one of engineering's most extreme achievements.